hit the record button. There we go. Okay, so we're diagnosing COVID-19, and the unique thing about COVID-19 is that it has RNA as its genetic material as opposed to DNA, which is what almost every other organism on planet Earth has. There's a bunch of viruses that have RNA, such as the HIV virus, but for all other living organisms, they use DNA as a genetic material. And the other thing that we need to acknowledge is that all living things have their own genetic material, a genetic code, and it's unique. So your genetic code is going to be different than my genetic code, is going to be different than everybody else's genetic code. That's going to be a key factor in all of this. And early on in the spread of the pathogen, in December and November, we sequenced the viral DNA, and that was a key bit. What this allowed us to do is this allowed us to know what genes are unique to, don't do that. Let's go back. I don't even know how I did that. Go back. That are unique to COVID-19. Okay, so we have those baseline bits out there. Moving on. The first thing that we need to do is we need to collect a sample from the patient. And this is primarily collected in two places. This is collected in the nose and mouth. And what they do is they stick a long swab to the back of your nose and throat. And the end goal here is to be able to get, not gent, is to get some viruses on the swab. Because what we want is we want the genetic material. Cool. First thing we do, stick a nose, and it goes way to the back of your nose and mouth. It's a pretty unpleasant experience. After that, we're going to do a process called RT PCR test. This is how we diagnose you with corona. This is how we're going to be able to say, hey, you have corona as opposed to flu, as opposed to a cold, as opposed to pneumonia. What these letters stand for are RT stands for reverse transcriptase, and then PCR stands for polymerase chain reaction. And I'm going to talk about these steps individually. And you can do PCR without the RT part, but there's no point in doing the RT part unless you're doing the PCR part. This RT part is step one. Step one is to convert the viral RNA into DNA. This is, in terms of a biotechnology thing, a relatively simple thing to do. You separate out the genetic material from everything else in the swab. And to do that, DNA has its own molecular weight. It has its own set of physical properties. In biotech, you probably do a really simple lab where you remove DNA from a strawberry, and you can have your own little necklace with, strawberry DNA in it, or your own DNA. It precipitates out pretty easily. So it's not a difficult thing to remove genetic material from the swab. Once we have that genetic material, we're going to use a protein called, quite conveniently, reverse transcriptase. And add a bunch of nucleotides to this mixture. And this will produce a DNA copy of the, oh, don't do that, of the RNA from the virus. So what we've done is we've produced DNA from RNA. Pretty easy so far. The PCR test is where things get interesting. For the PCR test, PCR already stands for polymerase chain reaction. And this is what we're going to use. We're going to use a protein called DNA polymerase. We're going to use free nucleotides that are labeled to glow. And we are going to use something called a primer. Now, this primer bit is going to be the most important part of this whole shebang. I'm going to wait a second to let you guys catch up because I see some of you guys writing. You guys can still hear me. Give me a thumbs up that you can hear me. Awesome. Okay. So what we have is, to make this a little more simple than it is, but for us to get the basics of it, is we have a beaker. And in this beaker, I'm going to have DNA. And I'm going to have DNA from a bunch of different organisms. I'm going to have the DNA from COVID-19. I'm going to have the DNA from the patient. And I'm going to have DNA from any other bacteria that we collected or anything else that we collected from the patient as we stuck this swab down this person's nose and throat. And then what we're going to do is we're going to add heat. And what the heat is going to do is it's going to take our double-stranded DNA and it's going to separate out all the strands into single strands. It does that because the thing that's holding DNA together are weak hydrogen bonds. And then what we're going to add is we're going to add those three other ingredients: the DNA polymerase, the free nucleotides, and the primer. And let's add those three components. Bloop. So I'm going to draw this beaker a lot bigger. So I have a little bit more space. We're going to add those three components. I'm going to draw this beaker a lot bigger. Now, here is the unique thing about the primer. And why it's so important. DNA polymerase can't build a new strand without a starter. What I mean by that is, if I were to add a DNA polymerase to a single strand of protein, it wouldn't be able to build a new complementary strand. Make sense? If you did this with no primer, nothing happens. So what we need is the primer allows the DNA polymerase to grab onto the DNA single-sided strand, to build a complete strand, a complete double-sided strand. So in my test tube, I'm quickly check and see what colors I had. I forget what colors I used. Orange and yellow. In my test tube, in my beaker, I have all this DNA that's now all separated out. Used orange and yellow, right? I used yellow? Yeah. No, I used orange and red. I need red. Okay. So I have these single strands of DNA. I have my DNA polymerase, and the primer is the critical bit. The reason why the primer is a critical bit is the primer is a short segment of single-sided DNA that only complements there's an E, not an I, complements the COVID-19 genetic code. What I mean by that is, if we have the COVID-19 going A, T, C, G, A, T, T, let's say, the primer, which I'll put in green, will only be able to match that short segment. So when we add this primer, the primer only attaches to the viral DNA because it doesn't match anything else. So this gives us a surface for my DNA polymerase to bind onto. So here my DNA polymerase can bind onto this section and build a new strand that way. Actually, I'm going to do that in a different color. Go back. Build a new strand in this direction. So this odd lime green color represents my new strand. This right here is my DNA polymerase. And this is my new strand. And If you repeat this process a bunch of times, you will only reproduce the viral DNA if the patient has it. So what you get is you get data that looks like this. Here's time. Here is amount of glowing DNA. Remember, those nucleotides have been labeled with a glow. If a patient doesn't have, is COVID negative, they don't have the virus, they're not going to be copying any DNA. But if the patient is COVID positive, as time goes on, we're going to make lots of copies of the DNA. And once you reach a certain threshold, you are positive for COVID-19. This whole process now takes a couple of hours. You can go to a testing center, and if they're not slammed with patients and they are doing the testing in-house and not shipping it out to a testing center, you can know within 5 hours whether or not you're COVID positive. Some of the issues that came up with COVID-19 in terms of the testing were the difficulty in getting enough primer and getting enough of the reagents and these nucleotides to build this new strand. The primer needs to be genetically unique and made to match only the viral genetic code. We only want it to match a very short specific sequence on the viral genetic code and not match the patient and not match anything else in there. Researchers have identified several genes that are prime candidates of being genetically unique. And so those are the ones that are getting copied over and over again. That's one reason why it took testing so long to ramp up, was simply a lack of materials. The other reason why it took so long to ramp up is not everywhere is doing this test, and funding wasn't available for it. Funding can come from many places, primarily the federal government, and they weren't putting their backs into it, and private industry wasn't putting their backs into it. You could pay for the test, and private testing centers were happy to take your $500 for the test, but most people would not be able to afford that. I'm going to stop the recording right now and let the people who've shown up ask questions. So give me 1 sec, everybody.